Let's look at the last sections for this course. We will focus on combustion pollutants. Okay, if you look at a given power plant, you may burn different kinds of fossil fuels. For example, if you look at 1,000 megawatts, that means the 1 gigawatt power plant, and you estimate the annual release pollutants from the burning gas, oil, or coal, you may have a different results. For example, you can do the comparison for burning natural gas, oil, or coal, and the emissions annual release you can find out can be find from this table. For particulate, sulfur dioxide, nitrogen oxides, actually you can find out coal always have a largest emissions on particulate SOx and NOx. Okay, and natural gas, when you burn natural gas, you have a less particulates and sulfur dioxide pollutants. But the nitrogen oxide, you still have a certain big value for the from the emissions, and but this is mainly caused by the thermal NOx influenced by the temperature high, and you can figure out oil has the largest emission for NOx in compared with coal. The NOx come from the burning coal. Basically is caused by the so-called fuel NOx. Actually, the nitrogen contents in the coal, but the gas when you burn the natural gas, actually the thermal NOx come from the high temperature. Okay, and the oil just add these two effect together. When you burn the oil, the temperature is also high, then they have a high thermal NOx, and sometimes, usually, the oil has a certain amount of nitrogen in its fuel set itself. Therefore, when you burn the liquid fuels, then you may have a largest NOx emissions in compared with burning natural gas or burning coal. And if you consider the carbon monoxide and the unburned hydrocarbon, actually, for the power plants, we treat these two species are the combustible species, which means if you do have the carbon monoxide and unburned hydrocarbon emission represents your system, the boiler do not have a good function to have a complete combustion. Therefore, you need to do some combustion adjustments. Then you can see for burning the natural gas, oil, and the carbon, actually the emissions for the carbon monoxide and the unburned hydrocarbon are very small, but still they have a certain amount of depth, right? For example, for the coal, because coal need to have a more good mixings, and they need to have a longer burning time. Sometimes if you have a local income, local pockets without good mixings, they will have a very small amount of carbon monoxide or hydrocarbon release. But usually they are very small in compared with other pollutants, for example, particulate SOx and NOx. Okay, this is a typical data for you to understand where is the pollutants, where are the pollutants, and what are the pollutants and emitted by the different fossil fuel. We will go through very briefly for some for the descriptions on different pollutants, and give you the idea and to learn what kinds of parameters controls the produce of the carbon produce those pollutants. The first category we were dealing with the particulates. Okay, when we look at the particulate, actually, they appear as the solid phase. Okay, especially they will occur in different situations. For example, they may deposit on the surface of combustion chamber. If, for example, the combustion chamber, the chamber surface of your diesel engines, and sometimes you can find the surface of the turbine blade when you burn when you use the gas turbine engine, and this is a typical observation on the existence for the particulates. They will deposit on the surface of combustion chamber. The other one, the size, if the size is very small, and they will flow with the backflows, and they will emit out through the exhaust systems. Then this is the other way, is emitted with the exhaust gases. For most of the combustion systems, usually you always have depend on your burning situation. You always have a certain amount of solid particles emit out. If you have a large amount of particulates, then you can see the exhaust become black, right? We call this the so-called smoke. But sometimes you cannot see it, but actually all the flue gas are coming out, but they still have a very small amount of particulates exist in the flow. Then that means it's not visible, but they still show you the very small concentration. And how come we can have those kinds of particulates through our combustion process and emit to the exhaust systems? There is three possible sources we can identify. The first one, especially this for the coal, they say they have some metals, then they should be burned, but they cannot be burned because they were not combustible. For example, for the coal, sometimes the coal compositions has a certain amount, a small amount of metal oxidizer or salts. Those kinds of materials cannot be burned through the combustion process, and they were just like a small solid particle emit out through the exhaust system. Okay. The second matter, which means that was capable of being burnt but was not burnt, actually this is related to the so-called the incomplete combustion. This always occurs in the combustion chamber because when we talk about a combustion process for the liquid fuel and for the solid fuel, they always need to have a so-called initial process. For example, for the liquid fuel, they need to have certain time for evaporation to produce fuel vapor, then go through the gas phase combustion. But for the coal, they need to have a surface reactions to release the carbon monoxide or carbon dioxide. Then they go to the next gas oxidation in the gas phase. They still need to have a certain time to finish the combustion process. And those completion on combustion process depend on the I just said the gasification process and also the mixing process, because when you have a hydrocarbon coming out, they need to mix with oxygen from the air. If the mixing is not properly controlled, then you will have a small pocket, and this pocket may contain too much fuel, and you cannot finish it. And when they go through the whole combustion chamber, they cannot complete combustions. Then it is a strong possibility to be a bit out. Okay. So this is a second category. Matter should be burned but not burned. Okay. For example, among hydrocarbon or some organic pollutants. Okay. The third one, okay, it is very special. They say the matter formed during the combustion process. That means the so-called, usually you can see from the flame. We call this a solid carbon. Why we can have these kinds of material, you need to understand the process of the nucleation of carbon. Later on, we will discuss. Those materials formed during the combustion process because for hydrocarbon fuel, they will absorb heat, and the chemical chain will be broken and to release the carbon atom and the hydrogen atom. In this process, carbon atom freely released from the original hydrocarbon fuel, but they will have a chance to meet other carbon atoms When they meet together, they will gradually they will grow and to become a solid particle, carbon particle. Okay, in this process, actually, they nucleate those kinds of solid particles in the thermal decomposition process of your fuel and in the combustion process. Okay, if you look at these three sources, actually, they tell you one, the part one, actually, this is more related to the composition of coal. And if you burn the natural gas and liquid fuels, you may not have too much metal oxides or salts inside of fuel. Then this part A should not be considered for burning natural gas and the liquid fuel. And B depends on the design on your combustion chamber. Do we have a good mixing? That means that from very earlier, I emphasize so-called there is a so-called 3T design. One is the temperature, the other one is the turbulence, and the third one is a residence time. And this 3T design will give you a control mechanism on the formation of those kinds of unburned carbon and relate to incomplete combustion. And the third one, basically, they are developed in the combustion process. Usually, you can see by different way. The first one, this is quite familiar for us. We call this a soot. Soot means the very small, tiny carbon particle exists in the high temperature zone. That means that in the gas phase process, then you can see the so-called yellow flame. Okay. The second is we call this as coal. Coke means those kinds of solid particles when they move because the combustion chamber is a confined chamber, and usually, especially for the automobile engines, they use the water to cool the combustion chamber surface has a lower temperature, which means that the temperature the surface of your combustion chamber face one part is very hot, the other portion is very cold. This temperature difference will give you a possibility when you have a irregular injection of liquid fuel, and those liquid fuel will attach to the to the combustion chamber surface, and since the surface on the on the surface side of the combustion chamber temperature are pretty high, then the liquid fuel will start to thermal pyrolysis in a very short time. Since in a very short time, they do not have enough time to separate, to cut down all the chemical chain for the carbon and the nitrogen. For the carbon and the hydrogen release very fast, but carbon in this short times, they do not have a chance to be released. Then they will attach to the surface to become so-called coal, and this is usually due to the irregular or unregular injections, and then the liquid fuel attached to the high temperature surface. Then they will produce the pyrolysis of liquid hydrocarbon fuels. Okay. Now, if you understand the possible sources for creating the solid carbon, then we now look at the presence of a solid carbon. Look at three categories you may identify. The first one, for automobile engines or other system with a water-cooled surface. Okay, I mentioned here, especially for the automobile engines, because for diesel engine or gasoline engine, both of them, because we use the size is small, and since the combustion heat release are pretty much high, they can push the piston moving and to generate the power. But inside of the combustion chamber, they need to have a certain they will have a big amount of heat exist, which means the materials of your combustion chamber, they will induce the high temperature. Usually the material cannot maintain these conditions at very high temperature, and they need to carry those heat out. For automobile engines, usually you use water, which means I just emphasize for a combustion chamber surface, one side by cooling water moving out, they carry heat out, but the other side is high temperature regions. But for the atmosphere, especially for diesel engines, when you do not have a good atomization, those liquid fuel will impinge onto the surface of the engines, okay, without complete gasification. Then liquid attached to the surface, and you will find out they do not have enough time to cut down all the chemical chain to produce a carbon and hydrogen atoms out. Then those thermal pyrolysis will push all the liquid fuel become coking, and those kinds of coking will produce a coke on the hot surface of your cylinder. The other one is a so-called gas turbine combustion chamber. For this combustion chamber, as we described earlier, those kinds of combustion chamber, the surface of the combustion chamber experience high temperature too, as the automobile engines experience. But for the aircraft, gasoline and gas turbine engine used for the aircraft, they are flying, right? And it is a good way to have some cooling, basically coming from the cooler air in the outer surrounding, right? Because you cannot carry a big water tank to circulate and to remove the heat out of the combustion chamber. It is better to have a cool air outside, sucked from the outside into your combustion, into your gas turbine combustor. As we described earlier, when you have a cool air coming from the compressor, then they will go through the gas turbine combustor by two-way. Primary air directly go in for the combustion, but there is a secondary air they are flowing and injecting through the near the surface of your combustion chamber for cooling. Okay, which means in these situations, and we understand for the gas turbine combustor, we need to have a good atomizer, and the atomization is pretty much good to produce the efficient burning. Then the soot formation may not very strong. They just have a small amount of carbon particles occurs. Small amount means they still have, but do not have a very large luminosity. They do not show very intense yellow colors. Then you still have a small particle, but those small particles will produce a severe problem for gas turbine combustors. I'm sorry for the gas turbine application, because at the end of gas turbines, the gas turbine combustion chamber, those hot flow will flow to the turbine, right? To the turbine. And if you have a small particle for the gas turbine, since the flow velocity are very high, even there is a small tiny particles, their momentum is very severe. If you carry those very tiny particle into the gas turbine, those small particles is just like a bullet, and they will impinge and inject onto the surface of a gas turbine blade. Okay, and they will cause the so-called pitting or corrosion of the turbine blades. And this is a major disasters for your gas turbine engines. You need to check the blade surface regularly to find out do we have any pitting or corrosion, because when you have a surface pitting or corrosions, they will give you the roughness and will influence the whole the flow structures. Then the power output will be reduced. Okay, this is a second category. The third one, and we try to look at for the industry furnace, the major features for industry furnace different from the previous two cases. Actually, they show you will have a large combustion chamber, and for this large combustion chamber, we need to burn a large amount of liquid fuel or coal to produce a large enough heat output to be used to heat. For example, for the boiler, we use those heat to heat the water from the room temperature to the superheat temperature. Later on, they can move to drive the steam turbine running. Okay. By this kinds of consideration means that if you think about a large combustion chamber, you have a large supply of the fuel into your combustion chamber, then the mixing definitely is need to be considered, but usually the mixing will extend for longer regions. Then you can see for the industrial furnace, usually you have a large frame and you have a so-called a luminous region in the primary zone. Then when you go to the further downstream, the luminosity will become weaker, and this is the so-called less luminous region. Now, if understand there is the two regions, one is the luminous, the other one is the less luminous, then you need to try to consider how to make arrangements to produce this big flame, because for the luminous region means the flame has yellow color, then the radiation heat transfer become most important thing for the design on this luminous region. But later on, for the less luminous region means the solid particle, the carbon particle is almost complete, then they release total heat to your flow. Then here the flow convection become most important compared with the radiation. Then by this kinds of understanding on the heat distributions in luminous and less luminous regions, then you can consider how to do the heat management for the heating from for example for the water heating, or sometimes you will heat certain your materials by using those kinds of furnace. Then which this is another different thinking, because you have a large range to let your solid particle be complete combustion. In the primary zone, you will let the particle exist and to burn as a yellow flame to have a stronger radiation transfer. But in downstream, you need to control it to burn all the particle completely and to diminish the luminosity. And later on, they will have a clean. I mean, a clean means the less particles emission out. Okay. Here, when I talk about the luminosity, means there is the simple test for carbon formation in flame is the luminosity. Okay, I emphasize the meaning of luminosity is the yellow color. Okay, because in the old periods, people use the oil for lighting, right? And when you burn the oil, the flame usually has the yellow color, and those yellow color give you the light. Then the people will say use the English name is the luminosity. Okay, luminous flame. Those luminous flame means the yellow color. Okay, and the yellow color radiation coming from the flames. They basically they coming from the dense phase of carbon. Remember this, because I mentioned why we will have a yellow color flame, because in that flames there is so many tiny solid particles they are burning. When you have a burning of a solid particle, then they solid particles, then you will have a observation on yellow color radiations. Okay. And when you look at the yellow color radiation, basically they will reveal two important facts. The first one, there is the indication of fuel-rich operation. Okay, in that region, in that yellow color region, you have a lot amount of fuel, including the solid carbon, and there is some of liquid fuel exist. Okay, and the second one is they will increase the rate of heat transfer. Okay, radiation heat transfer. Okay, now the luminosity is basically reflected two important facts. One is the fuel rich, and the other one is the strong radiation heat transfer. Okay. Now we try to look at the mechanism of the soot formation. The soot formation actually coming from the pyrolysis of your or decompositions of your hydrocarbon. Okay, then you will find out there is the two competing rate of reactions. Okay, one is the forming soot, right? Because you have usually the natural gas and oil or coal, they are hydrocarbon. When you put those fossil fuel into your combustion chamber, they will experience a high temperature. Then the first step, they need to cut their chemical chain to release carbon atoms and also hydrogen atoms. Okay, this is the first step. They need to have a so-called decomposition, and the rate of those decomposition is a key factor because they will release carbon atoms. The other chemical reaction rate that you need to consider, because those carbon release coming out, they will meet with oxygen coming from the surroundings, from the air, and then they will start to so-called have oxidation. This is another competing chemical reaction rate. Then you can think the decomposition of hydrocarbon will form in soot. This reaction rate will be compared with the oxidation rate through the through the reactions of the oxygen coming from the air and also the carbon. These two reactions, they are competing. Okay, if the forming soot is stronger, then you will have a large soot. If there is this, if the soot, if the oxidation rate is stronger, then all the soot will be convert to carbon dioxide or carbon monoxide very soon. Okay. This is the competitions on two different kinds of chemical reaction rates. And the second one is still very important, means the residence time. Residence time means in a given control volume, actually, the species exists in this control volume. Usually, they just can stay a certain time interval. Do we have enough residence time for complete oxidation or complete soot productions? Then you need to check it. And from our experience, actually, the residence time is too short. You may not have a soot occurs. Too long, you will produce a complete oxidation. They just have a time regions, the residence time region, and just suitable to produce a soot formation. I give you an example. As I described for the jet diffusion flame, right? For you remember, in the base, for the base of your diffusion flame near the exit plane of your burner, usually you can see there is a blue flame, right? And I emphasize in this region because the jet just coming out, the old jet has higher velocity. Higher velocity means the flow in these regions has the smaller residence times. The fuel cannot stay in this region too long. In the case, in this region, if you do not have enough residence times that the fuel stay here, they do not have enough time to cut down all the chemical chain to release carbon atom out. Even you can have some carbon atom coming out, they do not have enough time to mitigate to produce a large carbon particle. But it is possible to have those kinds of nucleation to have a large soot particle in the downstream because flow velocity becomes small. Okay, now you understand why the flame the flame on the base of diffusion flame has the blue color. This is one thing because residence time too short. The other one is I mentioned there is some additional oxygen entrainment from outside. The supply of oxygen is large enough, then the soot, even you have a small amount of soot coming out, the carbon atom coming out, they immediately react with oxygen, then finish it. Okay, then you will not have a soot. Okay. And if you go to the further, for example, a good mixings, and you have a particle, soot particle. If, for example, I mentioned for the industry furnace, since the combustion chamber is pretty much long, when you go to the very far downstream sites, you have a more oxygen exists in the environment, but your fuel become less, right? And you will have a more time and a good mixings with oxygen, then they will have a complete oxidation for the soot. Okay. Now, if you look at the problem for the production of for the soot formations in different kinds of application, you can go through these two directions to think about the competition between the rate of reaction for forming soot and causing its oxidation. And you still need to consider the residence time based on the mixing considerations. Now let's look at how to create the soot. There is a several step. Okay, the first step we call this as a nucleation. Okay, as I mentioned, they need to go through the gas phase reactions, produce a condensed phase solid nuclear. The first step they will go for the step one. They will go through by this way. Thermal decomposition of the hydrocarbons, okay, especially for the organic compounds, okay, you have a hydrocarbons, you need to absorb heat to cut down their chemical chain, which means that we will go through the hydrogenation, okay, release atomic carbon or C2 radicals, something like that, okay. And those carbon atoms include carbon and the C2 radicals, they will have a chance to mitigate then there was growth. Okay, growth is the so-called condensation becomes a solid particle. This is the first step, the nucleation for the solid carbon particles. Okay. And here there is some detailed observations on the molecular structure of carbon particulates. Can you go through it without? I think this is just for your information on the molecular structure of a given carbon particles. You can try to look at it and try to see the scale of different kinds of situation. Now we go to the step two. Now, step two means now you have a very tiny, small particles, right? And when you have those small particles, then you will face two different kinds of competition. One is if you two have two molecules, two particles, they hit together, then the size become large, right? But the other way is they have a chance to meet with oxygen, okay? Now, those oxygens will suppress the soot formation because they will have a surface reaction, and they will reduce the carbon luminosity. Okay, since even you have a carbon, just like a burn the coal particle. You know, when you have a coal burning, you always have a surface reaction on the coal surface. And similarly, for a carbon particle, you can figure out there is a surface reaction between the carbon atom with the oxygens, okay, and those oxygen will dig those kind of carbon to produce a carbon dioxide or carbon monoxide to out of the coal particle and go into the gas phase, and we call this as so-called heterogeneous reactions. Okay. And we find out from the literature the presence of free valence can catalyze such reaction on the surface of this nuclear. Okay, those carbon particles. And the step two, they will have a heterogeneous reaction. The step three, actually, the competition occurs between the step two and the step three. Step two means those kinds of oxidations on the particle surface will make the solid particle become smaller, right? But for step three, they tell you if those kinds of separations on the soot formation is not too strong, then they will have a possibility to have a so-called agglomeration and coagulation. Agglomeration or coagulation means that you will have several particles, they are moving and they have a chance to meet together. Especially important for the downstream, for example, I mentioned in the downstream of your jet diffusion flame, because you push all the particles move to the upward, and in the downstream of your jet plant, and the velocity become lower, and they will have a chance to interact and meet together and have some agglomeration and congregation. Then this means that your particle become larger and larger. And I think you remember from the candle flame experiments, you can see there is the break line go through the tip of your candle flame, right? They were coming out. When they see there is a line of a past line of the break particles, that means the so-called the smoke. It's a small one, but for the large emission from the power from the plant, and they were big one. Okay, and this is step 3. And those kinds of agglomeration and propagation actually is a relative slow compared with the other two. Okay, if we give you some concluding remark for this three step, actually, the first step it basically tell you how to create how the co-particles are new created through the those kinds of process. They are controlled by the chemical reactions through the decomposition of the hydrocarbons and also dehydrogenations, and those are controlled by the chemical reaction rate. And the second basically occurs on the surface reactions. Actually, they're relatively slow but still fast compared with the last one, because this is a combination, and the configuration actually is controlled by physical structures, by the mixings, by the flow velocity, okay, which is a small one compared with the other two. The subsections for 3, we try to look at a certain physical and chemical parameters on soup formations. Okay, now I give you a short summary on soup formation, and the 2 factors you need to consider for the soup formations for the in the gas flow, even for the diffusion flame and the premise flame. Basically, they were controlled by the molecular structure of the fuel. The fuel structure, molecular structure of the fuel is one of the important factor. The other one is the so-called competitive reaction rate. One is the soot formation. The other one is the soot oxidation. Okay, soot formation means you form you form the soot through the decomposition of your liquid fuel, right? And oxidation means you have oxygen come in, and they will react with the your carbon particle, and these 2 reaction rates, they are competed. Okay, now for the soot formation, you need to consider these 2 major controlling factors, and then think about how to look at it and control these 2 factors. And sometimes you need to prevent the soot formation. Sometimes you need to understand how to manage for soot formation. In general, for diffusion flame, they always have some luminosity and form soot relatively easier, okay, because the fuel separates separates from the oxygen by the diffusion flame itself. It is hard to have a soot particle simultaneously have large amount of oxygen, because all those soot particles, carbon particles, exist in the same region, and they are easily to be coagulate, and becomes a large radius of the particle, and this produce a very difficult to oxidize or to have oxidations. And because there is always a zone very close to the flame beneath a high temperature means they will promote decomposition of your hydrocarbon to release the carbon atoms. And the second one is there is very high carbon to oxygen ratio, means you do not have some oxygen that exists in the fuel side to initiate the oxidation. These 2 facts will promote the nucleation of your carbon particles. Therefore, you always have a carbon particle exist inside of your diffusion frame in the field-rich region of your diffusion frame. For premise frame, usually the fuel will mix with oxygens. For this case, you almost do not have a chance to have the carbon particles exist. But for the premise frame, there is the one condition you may have a soot particle occurs. That means the premise frame must be very fuel rich to become luminous and soot. Okay, these are conditions you need to understand. Okay, now we separated to discuss a certain controlling factor for diffusion frame and premise frame. Let's first look at from around diffusion frames. Molecular structure is one of the important factors you need to consider. From the literature, they find that there is several rules to identify the formation of a subparticle by through the molecular structures. The first one, people found that naphthalenes and larger than benzenes, ethylene, and diolefins, normal olefins, than paraffins. Paraffins has the less soot formation if you go through the diffusion burning process. Okay, and you can find out if you have a single chain for the paraffins, they need to absorb more heat for cutting all the chemical chains. But for example, there is a double chain for the benzenes and ethylenes. Ethylenes has a double chains. Those double has a unsaturated hydrocarbon. Usually they will release carbon easily in compare with the total, and that means the carbon hydrogen ratio. Carbon hydrogen ratio means the carbon the carbon weight compared with the hydrogen, how many or numbers in the fuel. If carbon hydrogen ratio high, it means that you have a less hydrogen compared with the other hydrocarbon fuel. And the other typical example shown by the second conclusion. Aromatic fuel has a higher soot formation compared with alkanes, and alkane. Here you can see alkanes has a single chain, right? And alkanes has a double chain, and alkanes has the triple chains. And especially for the alkane has the lowest soot formations. And the third one, we find out that the branching reactions, branching compounds has a larger carbon subparticles compared with that for the straight chain compound. You quite understand, because when you have a branch chain reaction compound, means the chemical reaction is very fast. The chemical reaction rate is fast. When you have this fast chemical reaction, they can release the carbon easily from the original hydrocarbon fuel. And for the paraffins, you can see if you increase your molecular weight, then the smoke will increase. Okay, this is caused by when you say the paraffin is a single chain, right? When you increase the molecular weight, the chain become longer. That means this will correspond the so-called compactness of the chemical. Since this is a long chain, then easily they will cut the chain between. Then they will release separately for the hydrogen atoms. Then they are easily to produce a smoke. The lowest smoke can be produced. Basically, is coming from the methane. Methane is always very compact, because the one carbon and connect with the 4 hydrogen atom, right? And they are perfect and arranged, and it's compact. Then you need to absorb more heat to let the hydrogen release. For the case, that means for the methane, it is very hard to see the yellow color frame. If you have an unsaturated hydrocarbon, okay, then you increase molecule weight. For example, for the paraffins, you have only one double chain, right? Then you try to increase molecule weight. That means that you increase one carbon with three hydrogen atoms, right? Continuously, that means that you will find out overall carbon hydrogen ratio will be reduced. When overall carbon hydrogen ratio reduced, then smoke reduced. Therefore, you can from those kinds of observation, you can have a very important conclusion shown by the sixth comment here. The principal factors controlling the tendency to soot are the CH ratio and the companies of the molecule. The CH ratio, as I mentioned, for different cases, for example, for the comment second, this is basically controlled by the so-called CH ratio, and also as we described the unsaturated hydrocarbon, you will increase molecule weight. Actually, that you will increase the carbon hydrogen ratio, which means that you will have a more chance to reduce the smoke. The companies or the molecule structure is the other effect. As I mentioned, for the paraffin, it will increase molecular weight more than the straight chain is continuous as the longer, and this is a longer chemical chain, easier to be cut, okay, to release the carbon radical and the hydrogen radical out, and they will produce the smoke more. But for the mixing, it's as the good companies, then it is hard to cut the carbon hydrogen chain, and they cannot easier to release the carbon out. Then the burning of hydrogens or methanes do not give us too much soot. Then the flame temperature, okay, if you have a higher flame temperature, now because we are talking about the diffusion flame, right? When you see the diffusion flame, the highest temperature will occur at the location of the diffusion flame. If you have a higher flame temperature, that means that you will have a greater, higher gradients, okay? And this higher gradients will promote, because in this side, fuel side, you have a lot of fuel here. Then the gradient of your temperature gradient stronger. That means that you have a more heat diffused to the fuel region. They will promote the decomposition of your hydrocarbon, then release the carbon. This is good for soot formation. Okay, but since you are very close to the diffusion flame, experience high temperature, this is one thing. The other thing is you are very close to the boundary of the boundary between oxygen and the fuel, right? Which means oxygen is easier to diffuse to the vicinity of the fuel site here, and this effect will promote the burning. Okay, now here you can see there is the two chemical reaction. They are competing. One is the soot formation, depends on the temperature, the flame temperature. Okay, the other one is the burning, depend on the distance away from your diffusion flame. Now there is two example I want to show you. One is for the methane. Since methane, as I mentioned, they are the methane, the chemical structure is very compact. You need to absorb more heat to release the carbon atoms. That means the carbon forms in the region of relatively high temperature. Since very close to the flame, near the position of highest temperature, flame temperature, which means they will have a chance to have certain amount of oxygen diffuse in, then they will complete the oxidation of your soot. That means you may have a chance to, you may not have a chance to have soot. Okay, then there is no soot. Okay, but for the ethylene flame, usually flame color is yellow because they will produce the carbon. They have a thermal pyrolysis, a thermal decomposition process slightly away from the diffusion flame, because they do not need to have a large temperature compared with the burning of methane. Okay, When they can nucleate the soot a little bit away from the diffusion flange, then the other factor, they will have a less support, a less supply of oxygen from the oxidizer side. This oxygen supply, and you will have a larger soot formation. Those factors just have a good chance to promote the soot formation. Then you will have a sooty flame. Okay, now for the turbulence, actually, if you have a good mixings, then you will control the soot formation or soot burning depends on the local pocket that you may have in your combustion chamber. As we will already give you some idea about the soot flame, the sooty flames, and the sooty flame can be produced in a counter rotating opposite flow. I hope you remember. Originally, the flame is blue, it's a blue flame, but when you increase the flow rotations, since you have a flow rotation, the swirling behavior will force the reverse flow flowing in near the stagnation plane, then they will reduce the residence time. Oh, I'm sorry. The flow velocity will be a flow inward and increase the residence time in this region near the stagnation plane, actually the field side of your diffusion flame. This increased residence time will promote the soot formation. Then you will see the yellow color exist when you increase the flow rotation as much as possible. Okay, this is just typical example to tell you when you control the flow structure, the turbulent AD motions, and you will have a local flow situation to promote the soot formation, or sometimes if you increase the residence time locally, they will suppress the soot formation. Okay, it is not easy to describe a major way to control the turbulence. But in general, when you have a good turbulence, that means you have a good mixings, then the flames usually has less soot formation. Easily, those particles can be react with oxygen through those kinds of intense mixing in the turbulent combustion field.